Hey everyone, welcome back to The Explainer. I'm absolutely thrilled to have you here today, because we are looking at something incredibly cool from Chapter 6. We're exploring the invisible, completely silent switches that safely control the high-powered devices we literally rely on every single day. So buckle up, because we are going to unpack the brilliant evolution of thyristors.
Just think about this for a second. How do you safely control a massive surge of electrical power? I'm talking about the kind of power that can drive a huge industrial motor or blast a giant electric heater. And how do you do it using only a microscopic pulse of current? You definitely don't want some massive, clunky mechanical switch that sparks and eventually wears out. No way. The answer actually lies in the fascinating evolutionary journey of a really unique semiconductor component. We started with something pretty blunt, and over time, engineers refined it into an instrument of absolute precision.
Okay, let's dive right in. Section 1. Introduction to thyristors.
So what is it? A thyristor, at its core, is a semiconductor device made up of 4 alternating layers of material. Specifically, it's a PNPN structure. And it turns out you can kind of think of it as a gatekeeper. By default, it acts just like an open circuit. It completely blocks current. It can withstand its rated voltage without even flinching. But the moment it's triggered, it suddenly transforms into this low-resistance path, allowing an absolute flood of current to pass right through. And the kicker? Once it's on, it stays on, even if you take away that trigger. Because of this super rugged behavior, thyristors are actually the hidden heroes, sitting right inside your lamp dimmers, motor speed controls, automotive ignition systems, and battery chargers.
Moving right along to Section 2, the 4-layer diode.
To really grasp this foundational building block, I want you to think of it like a stubborn, heavy door that you literally have to ram open. If we break down that PNPN structure, mathematically and electrically, it behaves exactly like 2 separate transistors interlocked together. You've got a PNP transistor at the top and an NPN transistor at the bottom. The collector of one actually feeds the base of the other, so they're locked in this continuous feedback loop. When just a little bit of current starts flowing, one transistor turns on, right? Which instantly forces the second transistor to turn on, which then feeds the first one even more. It's this incredible runaway regenerative action. Now here is what that whole process looks like plotted on a graph. Follow the bottom axis with me over to the point labeled forward breakover voltage. Now in the forward blocking region, the device is practically an open switch. It's totally resisting the flow. But if you just keep cranking up that voltage, you eventually hit that breakover point. And boom! This is the exact, highly visual moment those internal transistors kick into that feedback loop. The voltage across the device instantly snaps back to a very low value, and it shoots straight up into the forward conduction region. We've effectively rammed that stubborn door wide open, and the current is just rushing through.
But there is a catch with the 4-layer diode. Once you ran that door open, well, you can't just easily pull it shut again. That runaway feedback loop we just looked at means the device is completely latched on. The only way to turn it off is to literally starve it. You have to reduce the current flowing through it until it drops below a very specific threshold. We call this the holding current. Once the power drops to just a trickle below that holding current line, the internal transistors finally lose their grip and the device violently snaps back into its high-resistance off state.
All right, Section 3, the silicon-controlled rectifier, or SCR for short. So the 4-layer diode is powerful, absolutely, but it's kind of brute force, right? You have to overwhelm the thing with voltage just to turn it on. Engineers quickly realized they needed a much more elegant solution. Basically, they needed to add a handle to our stubborn door. And that's the crucial difference here. The basic 4-layer diode only has 2 terminals, an anode and a cathode. It's triggered entirely by brute forcing that breakover voltage. But the SCR, it takes that exact same PNPN structure and adds a 3rd terminal called the gate. This is our handle. So now, instead of pushing the main voltage all the way to the breaking point, we can hold a massive voltage back with the SCR and open the floodgates gracefully using just a tiny, precise little electrical pulse right at the gate terminal.
What's so brilliant about this is how we can bring it to life with an incredibly clever variation. It's called the Light-Activated SCR, or LASCR. Check out the alarm circuit here. We've got a light source beaming across a doorway straight into the LASCR. As long as the light is hitting that thyristor, it acts like a steady gate trigger. It keeps the current flowing and the relay coil totally energized. But if an intruder walks through the door and breaks that beam of light, even for a fraction of a second, literally, the LASCR loses its trigger. The relay clicks over, the alarm sounds, and because of how the circuit is wired, it stays sounding until someone physically comes over and hits a reset button. It's perfect if this, then that logic, and we didn't even need a single line of computer code to do it.
And that brings us to one of the absolute most common applications of the SCR, which is alternating current, or AC, power control. In this schematic, we have an AC power source and a load, like a lamp or maybe a heater. By just tweaking that potentiometer, the one labeled R2, we're actually changing exactly when the gate gets its trigger pulse during the AC wave cycle. We can trigger it super early to give the lamp almost full power, or we can trigger it late so only a tiny little slice of the AC wave actually makes it through, which dims the light drastically. It's effortlessly chopping that power wave to give us completely variable control.
Okay, let's keep moving. Section 4. DIACs and TRIACs.
So here is our next big problem to solve. AC power flows in two directions, right? Positive, then negative. But the SCR only allows current to flow in one direction, which essentially wastes half of the AC wave. We really need a swinging door that opens both ways. The first step to getting that bidirectional control is the DIAC. Notice its mirrored internal structure here. You've got an NPN-P structure facing one direction and a PNPN facing the exact opposite way. It's basically two 4-layer diodes wired in parallel, opposite to each other. And because of this setup, the VI curve is perfectly symmetrical. Whether the voltage pushes forward or pulls backward, once you hit that breakover voltage in either direction, the DIAC just snaps right on and conducts.
So the really crucial point is this. Just like we evolved the 2-terminal 4-layer diode into the 3-terminal SCR by giving it a gate, well, what happens if we take our bidirectional DIAC and add a control handle to it? You guessed it, we get the highly versatile TRIAC. It's essentially a switch that can conduct AC power in both directions completely under the command of one single gate terminal.
I mean, this is just a thing of beauty for electrical engineers. Notice how in both the top right positive quadrant and that bottom left negative quadrant, there are actually multiple breakover curves. As we increase the current applied to the gate, the voltage required to break over and turn the switch on drops significantly. This means we can dictate exactly when this dual-direction switch fires. We can delay the angle of conduction on both the positive and the negative halves of an AC wave. That gives us incredibly smooth full-wave power control for everything from heavy industrial machinery down to the dimmer switch sitting in your dining room right now.
And finally, Section 5. The Silicon-Controlled Switch, or SCS. So we started with a door we had to ram open, then we added a handle. With the SCS, we are literally putting handles on both sides of the door. Notice the schematic symbol here. It features your standard anode and cathode, sure, but it now has two distinct triggers, an anode gate and a cathode gate.
Now, why does this actually matter? Why even bother adding a second gate? Well, if you think back to a standard SCR or TRIAC, remember that once you trigger it on, it stays on until the main power supply drops below that holding current. You simply can't turn it off with the gate. But the SCS, it totally changes the rules. Because it has access to both halves of that internal transistor feedback loop, you can apply a pulse to one gate to turn it on, and then send a completely different pulse to the other gate to forcefully turn it off. It interrupts the current instantly, no waiting for the main power to drop. This makes the SCS incredibly fast and just absolutely perfect for digital applications, rapid counters, and precision timing circuits.
It's amazing when you zoom out and think about it. We've gone from a simple 4-layer slice of silicon that blocks current to these highly complex, multi-gated switches that can process light, dictate precision timing, and effortlessly throttle multi-directional industrial power. And they do it all without a single mechanical moving part to ever wear out. It's honestly a phenomenal feat of semiconductor physics. So I want to leave you with this thought. If we can achieve this insane level of microscopic control over massive amounts of power today, what invisible switches will power tomorrow's next great technological leap? Think on that, and I will see you in the next explainer.